Hi, I hope your week is going well. This video will explain how to design the filters for the lab 6 where you're designing a crossover filter design. So essentially in this lab, one of your headphones will be connected to a high pass filter and the other will be connected to a low pass filter. And those filters are the ones we're looking at designing in this. Now the way I'm going to show you how to design the filters in this video is using the resistance from the earbuds as part of your filter. So you'll notice there's this coil of wire here, and that coil we can model as just a resistor in our circuit diagram, and I'm going to call it RH. So whenever I refer to RH in this video, I mean that resistance from the coil in the headphones. Alright, so let's take a look at one of the topologies we can use. This is a CR topology. It's called that just because it has a capacitor and then a resistor. One important thing to note when you are looking at your filters is which component Vout is across. So in this case we have the headphones and we care about Vout across the component. For this lab you're going to have Vout always be across the resistance of the headphones. So just keep in mind which component in the circuit that is. Alright, so our transfer function, we have Vout, we'll start with the voltage divider equation. Vout equals Vin times the voltage of the component we want the voltage across, so that's RH in this case, over the total equivalent resistance. So RH plus 1 over j omega L. The next step would be just to get it in the form of Vout over Vn. So that's pretty simple. It's just RH over RH plus 1 over j omega L. Now we want this function, this transfer function, to be in the form of some equation that has an omega over omega c in it. And when I say omega c, I mean omega subscript c, not omega times c. That can be a little confusing. Omega subscript c is the negative 3 dB frequency, or also known as the cutoff frequency or corner frequency for your filter. So to do that for this equation, I'm just going to multiply everything by j omega L or j omega c. So I would get RH j omega c on top, and then RH j omega c plus 1 here. And that's just because multiplying everything by j omega c, that canceled that, so you just get a 1 there, and then these both are the product of j omega c times RH. So that's how we get this here. Cool. Now if you look at this and think about it, if you chose omega c to equal 1 over RHC, then you would get j omega times, or j omega over omega c equals j omega over 1 over RH times c, which just gets you j omega RHC. And this is the same thing we have here and here, so that works. And that means our cutoff frequency is 1 over RH times C. Before we move on, let's think about what kind of filter this is. So I want you to think about this in terms of what the filter does at low and high frequency, and specifically what the reactive component does. So at low frequencies, this does not allow current to flow through. So there's no current flowing through this resistor, which means Vout is just 0, because V equals IR for a resistor, so no current means no voltage across that resistor. At higher frequencies, this frequency increases, the impedance of this capacitor goes to 0, and so more current flows, which means more current flows through this, and Vout approaches Vn as frequency tends to infinity. Oops. So this is, because it passes high frequencies and it blocks low frequencies, This is a high pass filter. All right, let's go ahead and move on to the LR topology. So this is very much the same, except now you've got an inductor in series with your resistor. Vout is still across the resistor and it's still in that part of the circuit. So if we go ahead and derive the transfer function, I'm going to skip the Vout over Vin part. I'm just going to skip straight to this so we don't have to do that initial division step. It's pretty similar. You'll get RH over RH plus J omega L this time. And again, that's just the resistance or the impedance, the component that we want the voltage across, plus the total impedance of the circuit. Again, we want this in that omega over omega C form, and remember omega C is the cutoff frequency, not omega times C. In this case, because we've got J omega L here already, and it's not 1 over J omega L, I can just divide everything by RH, and then I will get 1 over 1 plus J omega times L over RH. And now if we choose omega C to equal RH over L, then if we did omega divided by omega C, we would get omega divided by RH divided by L, which is just equal to omega L over RH. And you can see that this is equivalent to this. So that is the correct cutoff frequency. So our cutoff frequency is RH over L. Cool. And let's think about what kind of filter this is. So at low frequencies, this inductor is passing current. It acts like a short, just a wire, which means all the current of the circuit's going across RH, and RH, or the voltage across that, will just equal Vn. And this is at DC. Now if we think about what happens as the frequency increases towards infinity, this becomes an open circuit, and so no current, there is no current flowing through this resistor, so Vout is just 0. In other words, because this allows DC or low frequencies through and blocks high frequencies, this is in fact a low pass filter. So we've got an LR filter, which is a low pass, and we've got a CR filter, which is a high pass. So you could just build your circuit with this, but there are actually a couple different ways to do it. You could swap the positions of the capacitor resistor or the inductor resistor, and you get slightly different results. So we'll look at that now. If you were to do that, they actually end up with very similar transfer functions. So we'll just go through that very quickly. For this RC circuit, Vout over Vn would equal, the important thing to keep in mind here is that our Vout node is still across this resistor. So it's not over here. We don't care about the voltage there. We care about the voltage across this resistor. That is fine though. That doesn't actually make the transfer function any more difficult. The voltage divider equation remains the same. It's just the component that we care about the voltage across divided by the total resistance, or in this case impedance, of the circuit. So that's our transfer function for this. And you'll notice that what we have here is actually the exact same thing we got for the CR circuit that we first did. So if we go back and look at that, our initial equation was RH over RH plus 1 over J omega C, and that is in fact the same thing we have here. So that tells us that the omega C is going to be the same. Omega C will equal 1 over RH times C. And you might guess the same thing happens with the RL circuit. So Vout over Vn equals RH over RH plus J omega L. And if you go through the math, you get the same result, where omega C equals RH over L. And let me just make sure that I did that right. Yep, RH over L. So these are in fact the same transfer functions. So if you use the same components, you get the same transfer functions, at least in this simple filter design. It's important to think about the functions of these filters as well. So let's think about the RC filter here. At low frequencies, this capacitor does not pass any current, so it acts like an open circuit. And the voltage at this node at DC would be Vn, because no current flows this way, so this node is the same as this node. However, that means that there is no current passing through this resistor. And if there's no current passing through this resistor, this voltage here is 0. And because we care about V out across this resistor, that means that at DC, this is actually blocking any signal coming through here. As frequency increases, more and more current starts to flow through here, and so more and more current is flowing through here, and the voltage drop across RH, which is our headphones, gets bigger and bigger, and more power goes through. So in fact, you realize that this is also a high-pass filter. Let me write that in red. So high-pass. And the same logic applies to this. At DC, this is flowing a lot of current through, so all the current's going through here because this inductor just acts like a short, which means this voltage drop here is V out is equal to V in. And then as the frequency increases, less and less current flows through here until it's open, which means no current is flowing through here, which means this V out is just 0 volts. So that means that this filter, the RL filter, is a low pass. Alright, now with that done, we'll look at a summary of what we found out. So here are our 4 filter types for filter topologies. We've got our high passes here with the capacitors, our low passes down here with the inductors. And I've gone ahead over here and written out omega c in terms, our equations for omega c, and then I've solved for C and L in terms of the other components in the circuit. Now in this lab, you're going to be asked to measure RH. That RH is the resistance of your headphones. So this is a value you know already. So all you need to solve for is L or C for your circuits. So I have gone through and picked a theoretical value for RH of, I set RH equals 20 ohms. And I said my cutoff frequency, FC, and this is in hertz, not in radians per second. Omega c is in radians per second, but you'll notice I have converted it down here from hertz to radians per second. I have said FC equals 1 kilohertz. This is just from my hypothetical scenario here. The lab is going to ask you for a different cutoff frequency, and your RH will probably be different. So make sure that you measure those. Regardless, if we go now to LTSpice, you'll see I have all of these circuits here. I've got the RC circuit here on the left. I've got the CR circuit on the middle left. I've got the RL circuit on the middle right. And this is the RL. And then this is the LR circuit on the left, or the right. So if I go ahead, and I think I've already simulated this, but let me just make sure. And I'm going to go ahead and start with the CR and LR circuits. If I probe this voltage here, which is the voltage across the resistor here, you'll see that it starts really low, and then it starts to pass right around 1 kilohertz. And in fact, if we follow that up to that point, and then we look over here on the left, that's right at negative 3 dB. So perfect, that's what we want. Now if we go to the same for the LR circuit, you'll see it has the same response, and I'm going to make this a little bit easier to see. Let's pick pink. You see it has the same response but flipped. It starts passing at low frequencies and then it starts to drop off, and right at 1 kilohertz it's reached that negative 3 dB point. So you could use, for example, this circuit and this circuit if you're trying to get a 1 kilohertz negative 3 dB point. It's a little more complicated to verify the RL and the RC circuits because if you remember, what we care about is the voltage across this resistor here and this resistor here, not the voltage across the inductor or capacitor. If you just measure this point here in LTSpice, it's just going to give you a flat voltage, as you can see here with this blue line, because that's the same node as the AC source, so nothing's changing. If you measure this one here, it's going to give you actually the opposite of what you're looking for. So if you think about the resistor, the voltage across this resistor is proportional to the current. So in fact, what you can do, let me just delete these traces so they aren't cluttering up our view. Go ahead and probe the current through this resistor. So if you just click on the resistor, it shows you the current. I'll do the same over here. And you'll see you get the same kind of response you want, and it's happening at the same frequency. It does not correspond to negative 3 dB. It's actually corresponding to much less, more like negative 30 dB. But remember that the current is not going to be the same magnitude as the voltage across the resistor. It has the same frequency response, and I think if you did the math to convert, for example, from this 20 ohm resistor, and you've got some current at like negative 30 dB, you would probably get the right voltage that you want. Anyway, this is the right frequency response, and if you remember that the voltage will be a factor of 20 times higher than the current, this works out. So, I hope this video was helpful for you in designing your filters. Again, if you have any questions, please reach out to your TAs, your ULAs, and hopefully this helps you succeed in Lab 6 and you do well in the rest of the class.